Um, questions about advection. So you had a question, go ahead.
Yeah, so for part one, we're using the first order upwind scheme for the whole of part one?
Yeah, for all of part one, yes.
Okay, so when part D, when the velocity is negative, we're going to have to switch around the scheme so that it's still upwinding.
Yeah, so the question is, for all of the subparts of question one, are you required to use upwinding? Yes, and the other question was, you're told to use negative velocity at some point, and for that, the stencil biasing will change direction. If you're using right biased or left biased, now it'll be right biased.
Okay.
So the point is, the code should be general enough that you don't have to write, you don't have to keep switching the whole thing, because in the domain you might have positive velocity in one region and negative in another region, right? So your code should be general enough that it looks at what the current velocity is and then uses the appropriate stencil.
Okay, that was my next question for part E when it's switching.
Yeah, so in part E here, it switches in time. So for a certain time, you'll have positive velocity, and then you'll start advancing in the other direction. So yeah, you cannot say, okay, the first part I'll simulate with this code, second part I'll simulate with the other code.
Okay.
The same code should check.
Okay.
Makes sense?
Yeah.
All right. And the second question is basically repeat all of the subparts above, but use a different upwinding instead of just phi I minus phi I minus 1. You use 3 points. So the only difficulty here will be what do you do at the boundary. Again, in 1D, it's not too cumbersome yet. In 2D, this will be a challenge. Okay, any other questions? I've lost my voice, so tell me if I'm to speak too softly. Anything else?
For part F, when I guess we'll be, it's downwinding, so it's going against it. Do you want us to write out the whole error calculation to show if it's unstable?
Okay, so part F is repeat, well, just run any of the cases above with downwinding, so the wrong stencil. And you'll see just after a few steps, the results go haywire.
Yeah.
So you can just run it until it goes crazy, and then stop there and plot back graph. That's
okay.
enough.
Cool.
Because if you let it go, eventually all the numbers will go to infinity, then your plot will show nothing.
Yeah.
This is due on Tuesday, I think. Today is Thursday, I think. Yes. Yeah. This is due on Tuesday, next Tuesday. Again, when you have, if you're stuck, have any sort of problem, email me or come to office hours. Okay. Anything else? Okay. So we have been talking about boundary conditions for velocity. Right, and we just mentioned that, okay, if we have a wall, we know what the boundary condition should look like. Okay? So what I'm drawing right now is actually one of the very popular test cases for making sure that your code works as it should. Okay, so you have a wall, and you can see what I'm doing. Yeah, all right. And this is a cavity. Okay. And what you do is you impose u equals something over here. U equal u lid is what it usually is called. So this is called a lid-driven cavity case. And it's sort of a very simple toy problem to test your code. So again, before we solve anything, what do we need to do? We should discretize our domain. Okay, so tell me, how do you want me to discretize this domain? Where should I put my grid points? Take a guess.
In the cavity.
In the cavity, okay? So you want me to put grid points inside here, not along the walls.
The walls which are in contact with, like, which make up the cavity.
Yeah, so since we want to solve for flow only inside here, we can forget about what happens outside. If you were interested in what's happening over here, you would put down points here as well. Okay. But right now we can say, okay, I can take this nice rectangular grid to be my computational domain. And the grid points are these. Okay, and now, if you forget about the physical setup, what you have is basically a bunch of points with boundary conditions given. At the walls, the velocity should be 0. At the top layer, the velocity is given. And we also talked about what the pressure boundary condition should be. Okay? So that's nice. Now, I keep saying the velocity at the wall should be 0. Do you believe that? So it's at wall, at any wall, u is equal to 0, b is equal to 0. Okay, so let's, if I have a flat horizontal wall, and this is x, and this is y, fine, it makes sense that the flow cannot go through the wall, right? That's physically impossible. But do you really believe that the flow will get stuck to the wall and it will not move? I mean, if you just take a bucket of water and spill it on the ground, it's not like it gets stuck, right? It keeps moving. So, first of all, if this does happen, why should it happen? Cannot go through because fine, there's a solid wall. But why should it not move along the wall? Physically.
Viscosity?
Viscosity. And viscosity is another name for friction. Right? So any water molecule that's trying to move along the wall, it experiences friction, which basically stops it from moving. And if you go even to smaller scales, if you start talking about molecules and atoms, what is friction? Do you know? Have you thought about it? If I try to move my hand along the table, there's some friction, but molecular scale, what is it?
Electromagnetic repulsion.
All right. Repulsion.
Not repulsion, but it's an electromagnetic.
Okay. So there. All right. So if I stand on the table, right, just stand on it without trying to move, I will not fall through. Okay. And that's because of electromagnetic repulsion. But if I start trying to slide across the table, my hand, I experience some force. That's not strictly due to electromagnetic repulsion. Maybe on a low level it is, but it's. Go ahead.
Yeah, because of the roughness of the wall.
Yeah,
There are
exactly. It's because of very microscopic imperfections on the surface. Imagine if there's a very polished surface, you tend to slip on it, right? You don't have any grip. That's exactly because these imperfections go away. So on a molecular scale, the same thing is happening. This wall is actually not smooth. It has many microscopic imperfections. Okay, roughness. And you know, the water molecules will come and get lodged over here, and that's why they cannot move. All right. So yeah, that's how we get that u equals 0 is a necessary condition. That's the no split condition, right at the wall. So if we just look at sort of a schematic representation, that's what's happening. If we look at different blobs of water or the liquid, so here the beads might represent different material elements or different blobs of water. The one that's in contact with the surface stays while the others keep moving. And the blob right next to it moves a little slower because there's viscous force in between these two. The blob far away can move freely. Okay? And if you still don't believe this, you can go and do an experiment. So what will happen here is, so there's, oh, what? Okay, wait. Come on. Okay. Okay, so the experiment we will look at is basically there's water flow in the tank, and there's a small tiny tube that will inject a dye or ink. Okay. All right. So there's the dye being released, and you can tell that the water is flowing from right to left. Okay. And you see everything that was released right at the surface sort of stays unless you come in and scrape it off. Okay. So the no slip condition is more, it's a valid condition to set in our simulations. All right, okay. So last time we also started talking about what happens if you don't have this nice rectangular looking body or walls. What happens if we have curved surfaces? So we looked at this and we looked at that, right? And we said, fine, we can just create body fitted meshes. Okay. And these shapes are very nice because mathematically you can do some sort of transformation to go from a rectangular grid to these shapes. But, you know, somebody comes to me and says, no, I want to simulate a potato, right? I have this weird potato shape. I want to see what the flow around it looks like. Okay. What should I tell him? No, this is not a nice mathematical shape. I cannot form a nice body fitted grid. I won't do it. Right? That's what I should say. No. You can actually form body fitted meshes for this as well. They won't be as nice. Well, yeah, I've never done that myself, so I hope you don't have to do it ever. And again, I say potato, but this might be an asteroid, and you might want to simulate the impact of the asteroid on Mars, hopefully not on Earth. So the other approach that you can use instead of, before that. So fine, body-fitted meshes work well for simple shapes. What would happen if I had these two shapes in my flow field simultaneously? Right? These are very two simple. These are very two simple shapes, and just having them next to each other, I would have to use a grid that looks something like this. Okay, so you see close to this body, if the grid conforms to it, and then it has to change to conform to the other body. This is a huge issue whenever people use body-fitted meshes. The grid gets all twisted, and cell sizes start going to 0. Even if you just had two circles over here, you would have something similar, because the other circle would need a different body-fitted mesh compared to that one. Okay? And now imagine that one of them, that guy, starts wriggling in time. So imagine you're trying to simulate how a fish swims behind a rock. Okay? So what will happen if I start wriggling here? You know what I mean by wriggling? You know, the body starts undulating in time, just like a fish would. What would happen?
The mesh would need to change.
The mesh would have to change at every time step. And creating these meshes is very heavy computationally. And when you do create a mesh, it often needs manual intervention. You have to go into regions where the mesh might be messed up. You might have to fix those manually. So if you decide to run an undulating body with a body-fitted mesh, first the mesh would need to be recreated every time step to fit the moving body. And this has to be done automatically. It's expensive, and you're not guaranteed you will get a nice mesh. Okay? So that's when people started thinking about alternative approaches. And this class of schemes is called immersed boundary methods. So there's immersed boundary methods, immersed interface methods. There's several variations of these. The basic idea here is you have your background grid that still looks like nice squares or rectangles. And then you have this potato over here, right? So that's just the surface of the irregular body. And all the black cells are inside the body, all the open circles are outside the body, and the gray shaded ones are the ones that can feel the influence of the body. Okay? And each scheme differs in how it will enforce this, enforce the presence of the body, enforce the influence of the body on these gray shaded areas. And that's basically what makes each scheme different. So if we look at immersed boundaries, for instance, let me see if I can. Alright, okay. So with immersed boundaries, if I have this were to be my, let's stick with a circle or a cylinder. So this is the inside of the cylinder, right? And I have my surface of the cylinder. Everything outside is in pure fluid. So first of all, you designate these points called ghost points, where you know the velocity, right? it's the velocity of the solid. If the solid doesn't move, this velocity is 0. And these are the fluid points where you want to find out the velocity. That's what you're solving for. What does the flow look like around the body? Okay. And what you can do is, you know what's happening here, you know the velocity over here should be also the surface velocity. And you can use some sort of interpolation to figure out what the velocity assigned here should be. Okay. So again, there's many different ways of doing these interpolations. You can look at the cells that are present in the grid, and you can take the surface cell, or you can say, okay, I want to look along the normal of the surface. Okay. And then there's this new cell where I have to figure out what the velocity is by doing interpolation from its surroundings. So there's several ways. Okay. And these approaches have issues. If you have a sharp corner, there's the issue of I might not have suitable cells surrounding me, so I don't know how to do the interpolation. And there's ad hoc fixes. Okay. But there's a much simpler way of doing this, which actually we use in the simulations that I have showed you before. The simulations of the fish swimming and the cylinder, flow across the cylinders. Okay, and that's called the penalty method. So it's called Brinkman. Okay, let me spell it out. Brinkman optimization. Okay. So what this method does is it adds a forcing term to the momentum equation. Okay? So let me write out this general forcing term. Okay, now I'm missing the viscous term. Okay, so it's basically the normal Navier-Stokes momentum equation plus an extra term, a forcing term. And if you think about it, this forcing term can represent many different things. If you're looking to simulate solids that are buoyant, this can be a buoyant force. If you're looking to include the influence of a solid boundary, this forcing term is exactly what we would specify. Okay. And in general, what does the left-hand side of the momentum equation represent? What is this?
Acceleration.
Yeah, it's the acceleration of the material element. Right? So the acceleration of the material element is usually due to pressure gradient, and there's a deceleration due to viscosity. Okay, and now I've added this forcing term, which will change the acceleration of my fluid. Right? So with penalty, what we do is we say this F, the penalty term, F can be set to chi US minus U. Okay, so it's a very simple representation. What are these chi and US and U, right? So U is basically the fluid velocity. US is the solid velocity. And chi is called the characteristic function. And this characteristic function is basically a mask. It's a mask that represents the solid object on the fluid grid. Okay, and this solid velocity can actually be composed of, could be made up of first of all, translation of the object, or what?
Rotation.
Rotation of the object, and there is an and.
Heats.
Twist,
Growth.
bending, growth, all of these you can put in here. But by growth, if you mean volume change, that becomes a little problematic because nabla.u equals 0 implies no volume change is allowed. Okay? So yeah, it's not very easy to simulate an inflating balloon or a deflating balloon. You can do it, but I mean, it's let's keep it simple at the moment, and we can say what we say. So growth is deformation, bending is deformation, right? So deformation of the object. Okay, and you might have a cylinder that's being moved as well as being rotated. Okay, so that would be these two components, or you might have that. How do I draw a fish? Okay, you might have a fish that's the center of mass is translating, the fish might rotate along the center of mass, but it's also, everything is deforming along the body, right? And the complete velocity of any point on the body can be fully described by combining these three things: translation, rotation, and deformation. Okay, and that basically goes up in here, in U solid. Okay, so all right, chi is characteristic function, U is solid velocity. What does that mean? What does that mean? Where is it? Not here. I should stop using the presentation. Okay, what that means is, okay, come on, away. All right, perfect. So if I have my solid at this location, that would be my potato, right? What I do is I set down my normal rectangular Cartesian grid everywhere, okay? And I will say, okay, I don't care about the solid for the time being. All of my grid points, I will solve my Navier-Stokes, as I usually do. The next step is creating a variable called chi, the characteristic function. And chi is equal to 0 when you have pure fluid and chi is equal to 1 when you have a pure solid. Okay? And you need to do something special at the interface. If you just say, I will have chi equal 1 and 0 and nothing else, you get this stair-stepping, as you can see here. We lose the smooth boundary. Okay? So usually what we do is in these intermediate cells, the interface cells, we smear out the interface. So the die goes very smoothly from 1 to 0. And it'll be some intermediate value, let's say 0.5 or 0.3 in these cells. Okay? And that's all. That's the only special treatment you need. Now what you can do is you can solve everything, all of the grid points, as if it were pure fluid. Okay. And this forcing term, F, that we talked about, it basically forces the occupied grid nodes to behave like a solid. Does that make sense? It might be a little confusing, so ask me if something's not clear. Okay, so we treat our whole domain as a fluid. We create this mask that occupies the place of the solid, and we add this forcing term only inside the solid, not the fluid. We don't touch. The fluid evolves according to the Navier-Stokes. Okay. All right. So that's exactly what's shown here. See, again, we have the Navier-Stokes, and that's the forcing term. Lambda is actually set to 1 over dt, so we can just ignore it for the time being. Fine, but what actually does this penalty term do? Just think about it for a second. Okay? If I am in the occupied grid points, in the green cells, after I solve my Navier-Stokes equation, will the velocity inside be the velocity of the solid or not? After I solve advection and diffusion, should I get the same velocity as the cylinder? Does this make sense or not? No. Okay. So when you solve Navier-Stokes, you can do the splitting, right? You can do advection, diffusion, then pressure projection. And I told you that you treat the whole domain as if it were a fluid. You forget about the solid. At the end of these 3 steps, at the end of pressure projection, is there any guarantee that the cell inside will behave like a solid? It will move with the same velocity as the solid?
It can be, it depends on the solid. I mean, it's not flexible, it's a
Let's say it's a rigid rock.
rigid rock.
Yeah.
So yeah, it should be the same.
You're saying it should be the same, but if you treat the whole thing as a fluid, and you solve advection and diffusion as a fluid, you know, it will behave as a fluid.
Yes.
Because you have not imposed anything, right? So after you solve this advection, diffusion, and pressure projection, the velocity inside will not match that of the solid, right? It's expected. It's another intermediate velocity. What this forcing term does is, see, this is exactly the difference. So that's the expected solid velocity. This is the actual velocity at the grid. Okay. And when this is equal to 0, this difference is equal to 0, the forcing term turns off. If this difference is non-zero, the forcing term will do something, right? Let's see what it does. So let's say the u here is slower than the solid u should be. This term is what? Positive or negative?
So I'm confused. The solid is not moving, or is it moving? It's fixed.
The solid is fixed, okay?
Solid is fixed, and we have a flow.
Let's say this solid is fixed and the velocity at all of these nodes, u solid, should be 0.
Should be 0.
Right? Now I told you, ignore that and solve for the fluid velocity in the whole domain. Okay? So I impose u infinity equal 1 meter per second everywhere. Okay? And what I'll get inside is 1 meter per second, which is not correct.
Yes.
So that difference exactly is this term. Okay? See, chi is equal to 1, and that 1 meter per second minus 0 will give me some non-zero value. Outside the green cells, everything will be 0, because chi is 0. I have confused you again. Forget about lambda for a second. Okay? I impose 1 meter per second on each cell, and you solve advection, diffusion, and pressure protection. During the first step, things will not change much. So what you will get is the green cells also have 1 meter per second, which is not correct. Right? The difference here, 1 meter per second minus 0, will be non-zero. Right? You have some non-zero difference, and chi is 1 inside the green cells. So you have some forcing term. And what that will do is, let's say, this will be negative, right? U solid is 0, U fluid is 1. So it will decelerate the flow very, very quickly. And that's what you want to happen. Inside the solid cells, they should decelerate very fast because it should go from 1 to 0. Okay. So now do you see what the forcing term is doing? And if it's the other way around, let's say I throw the rock and it's moving through air. Air has 0 meters per second. The rock has 5 meters per second. U solid is 0. U solid is 5. U of the grid is 0. So the forcing term will cause things to accelerate in the green cells. Does it make sense?
Yes.
Okay, all right.
But the only thing is, in the beginning, why do we mathematically add this? This is called ad hoc term? What is it?
This is called a forcing term.
Reinforcing.
Yeah.
So, are we allowed to add this term and then interpret it? I mean, mathematically?
How
like an
else
stuff?
would you do it? The only other way to do this is to have a body-fitted grid, where you don't have to add any forcing term. You just solve for fluid, the velocity on the grid points. And the grid points would lie exactly on the body, and then the surrounding grid points would also conform to the shape. But for very complicated shapes, that's not an option. For deforming shapes, that's not an option. Even for moving and rotating shapes, that might not be an option when you have only 2 objects. Think about if you have a school of 100 fish and you try to simulate it. It just gets out of that. Okay? So this is an easier alternative. It's not as accurate, but things that were impossible before now become feasible to do. Okay? And this is a very simple thing. And surprisingly, it works very well. The only disadvantage is that you have to have a lot of grid cells because, if you have a very curved surface, then you need to have a lot of grid cells here to minimize this sort of stair-stepping. And that's the main source of error, the smearing of the interface. Okay. So that's why we usually use this sort of adaptive grids in space and in time. The boundary, wherever there's a solid boundary, you make sure there's enough points that the smearing is almost invisible to the solver. And far away, you don't care. Okay? Does it make sense now? All right, so let me see. Yeah, go ahead.
So, how do we implement deformation and rotation here for for the solid body?
Yeah, okay, so let's see. If we go back to the paper. Okay, so it's clear what this term is. Now, if your solid body, let's say my fish, is Okay, so let me draw a bigger fish. Okay, and this has the green nodes inside and blue nodes inside. Okay, and then there's nodes outside in the fluid, which are not blue. Okay, only the blue nodes have chi equal 1. The black nodes have chi equal 0. Is this okay for up until now? Okay. Now, how would you, when you do a swimming fish, what do you do? What do you impose? In a natural sense, what does the fish do? Does it, on its own body, does it impose a rotation and a translation instantaneously, or does it do something different?
No. Yeah, it's a combination of translation, rotation.
No. See, the translation and rotation is an outcome, right? Initially, the fish just starts undulating its body. If it starts undulating in vacuum, it will not move at all. There will be no translation nor rotation. Does that make sense?
Yeah.
So the only reason it starts moving forward and starts rotating slightly is because the fluid is acting on it. Okay. So in the simulation, what we do is we just impose the another color. We just impose the deformation of this one, this body, U dash, and my U solid in that case becomes U translation plus U rotation plus U deformation, and these are 0 initially. Okay. When we impose this deformation, in a very crude sense, the body pushes fluid around, there's a reaction force, and then it starts moving forward because of the reaction force. And when it starts moving forward, you will have this ut and ur non-zero, and then you would use the full thing. Okay, and u def is, it looks like a sine kx minus omega t. In a general sense, so what you do is at each of the blue points, you figure out the deformation velocity. So each point has a different value of u def. But that doesn't matter because in my formula is very general. So us at different i's would be different, and at those grid nodes you would enforce the required ui. Does this make sense?
Yes.
Okay. All right. Yes, ask.
But I think in rotation, we change that force into x times omega s minus omega. Is that how we look at in the equation?
In rotation, you change the force to what? It's s time. Can you say that again?
Instead of us, we use omega s. And
No. Okay.
Rotation.
Yeah, I get it.
I think you have it in the next slide. You had it.
I had it in the slide.
Yes, I think.
No, I don't see it here.
No.
I will put it up, but okay. So it's a simpler example, and it will make more sense. Okay. So let's see. Suppose you want to do this with a rotating cylinder. Okay? The cylinder is not allowed to move. It's just rotating. I actually have a video I will show you. It's nice to have videos, but they won't. Here. Okay. Where is this one? Fine, this one first. So what will happen here is, okay, imagine the fish is being simulated by some method, but what will happen here is this cylinder starts oscillating at some point. Okay? What I did in this case was, again, these grid points are occupied by chi equal 1 and u solid equal what I impose. So what I impose is these grid nodes have a sinusoidal velocity, all of them. And in time, my patch, the green patch moves. Okay, so new grid cells will be occupied by the solid. As it moves, it comes back. Older grid cells will be occupied by the solid, and that's exactly what happens. Okay. So this motion is completely imposed by me. I say B equals 0, rotation equals 0, U equals something, non-zero value. Now, in another case, what I did was I did pure rotation, no oscillation, no. Okay. So in this case, the cylinder will rotate. And the color you see is vorticity. So all of the grid cells instantaneously change vorticity value. The cylinder rotates that way, so the fluid gets a negative vorticity. Everything makes sense. And what I impose here is that exact constant omega value. Okay. Each point inside the cylinder has some omega value. And once I know the radius, I can change it into U and V components. And that U and V is what actually gets imposed on the grid. Does this make sense?
Yes.
Perfect.
But I still have a question. In that method, the grids are not moving, are fixed.
The grid can be fixed, yeah. Your object might move. So
The object.
when I have to keep switching back and forth. So here. So you remember when I made the cylinder oscillate?
Yes.
You can take this potato and make this oscillate. What would happen is this green cell moves onto this. So this new cell becomes green.
Yes.
The old green cell becomes white. That's it. You're just moving your chi field. Okay? And that's
But the location of the grid doesn't move. We are just defining as
Yeah.
S or F. S.
Exactly. The grid need not change. In the simulations that we use, the grid changes, but that's for computational reasons. Conceptually and implementation-wise, the grid can stay constant, just like here. Only the green patches have to move left and right. I mean, new cells become green, older cells become white from green as the solid moves away. Okay. Is this clear now?
Maybe another question.
Yeah.
Not related. That cylinder and fish, they didn't have any interaction with each other.
They did
Just
actually.
like-
Yeah, they
I
do.
didn't
So you can
notice.
see that. Good, yeah. You will notice that they do interact.
That is.
When the fish comes close by, you will see non-zero vorticity starting to develop on the cylinder. Okay, when it's far away, you don't see anything, but now it's getting close. You see, there's a red and there's blue. Here. Everything was white at the cylinder, and slowly you get very weak vorticity develop. That's because the fish is swimming by. Okay.
So the cylinder is free to rotate freely.
No.
No?
For this very specific case, that's the experiment I was doing, simulation experiment, that the cylinder does not get displaced because of the fish. It is at this position, and at a very specific time, it will start rotating. Okay. And the goal was to see how this disturbance is sensed by the fish over here. Okay. Another experiment that you might say you're interested in is the cylinder can get pushed about by the fish. So as it swims by, you will see the position of the cylinder changes a bit. That's also a possibility. That you know, I had something specific in mind, so that's how I did it. Make sense?
Yes.
Yeah, go ahead.
So, How do you choose that lambda parameter there in the forcing penalty term?
Yeah, so this lambda parameter, it's, so some people used to say that set the lambda as large as you can, because then what happens is the forcing term is very aggressive. Any difference is very immediately taken care of if this is, let's say, 1 million. Okay, but from experience, I've come to realize that you set lambda equal 1 over dt. So every time step, you have a particular dt that's governed by CFL conditions and other things. And when you set this lambda equal 1 over dt, that will cancel the dt when you bring it from the other side. Okay, so long story short, lambda is said to be 1 over dt. And
Okay.
some people call this the, what is it called? The DLM, discrete Lagrangian method. What? It's called DLM, I forgot the full form. Okay. So yeah, different people have used different ones. I prefer using 1 over dt.
Thank you.
Sure. And that's necessary to make the whole thing dimensionally consistent. See, this is velocity, velocity, chi has no dimensions. On the left side, we have velocity over time. So lambda equal 1 over dt makes sense. Yeah. Okay. So yeah, this is a very, very simple and very elegant way of imposing the boundary conditions for irregular solids. You can even do the same with walls. You know, wherever you have a flat wall, you put those grid points as u solid equals 0. That's your boundary condition. And then again, solve the whole thing as your fluid. Okay, any other questions? All right, so as I was mentioning, you know, there's this issue of stair stepping, which can lead to inaccuracies because of oscillation. Due to oscillations, numerical oscillations. So here you would have chi equal 1, and then immediately next to the surface you would have chi equals 0, which is not good. The derivatives would be huge. So yeah, what we do is we regularize the surface. Or you can say, okay, if we look at it in 1D, if you have a pure solid block, right, the chi here could be, let's see, what is the best way for me to show you this? Okay, so sharp chi field would be, you have 1, 1, 1, and then immediately you have 0. This is solid and you have fluid. Okay, so the profile, the change in chi will look something like this. Right? So with a smooth chi, what we do instead is we say, okay, fine, this one stays as 1, 1, and then this will not exactly be 1, it will be, let's say, 0.8. The next one will not be 0, it will be, let's say, 0.3. And then you have 0 and 0. So what you get is you have solid, and then the interface gets smoothed out. better for pneumatics, better for numerical stability. Yeah, if you jump immediately from 1 to 0, the derivative here tends to be very large. So it's nicer to go with a smooth transition. Okay, and there's very simple approaches to implement this. For instance, you can say there's a cosine function that decides my transition from 1 to 0. So it will be a smooth curve that's infinitely differentiable. Okay. And all of these issues happen because we have to discretize. If we were doing continuous mathematics, we wouldn't need to worry about these things. But we cannot, because no analytical solution for FAU slopes, and computers don't only understand discrete stuff. Any other questions? Okay, so let's see. Well, let me show you some more examples of simulations that you can do with these methods. Well, one particular example. And then we'll start talking about vortex methods. Okay, so let's see. This was just some very simple simulations we were working with, looking at heaving of airfoils. Airfoils, all know what airfoils are? Okay. So yeah, we had an airfoil, and there's something interesting that happens. If you take an airfoil and just heave it up and down, it'll start moving forward. It's called the Knoller-Betz-Meyer effect. And there's some very cool things about why it happens. So there's a vortex that forms over here, and it's it moves backward, and you can look at the force distribution, and you can actually see that the forces are towards the front. They're pointed in the forward direction, which will make you start moving. Okay, and then you can start analyzing what's happening. You can look at FTLEs. These are called FTLEs, finite-time diagonal exponent. They basically are separation lines. They show how fluid on this side, which cannot jump over to the other side, and likewise, vice versa. Okay. You can even do particle tracking. So what happens to particles, to fluid blobs as the airfoil moves. So here's the initialization of the fluid blobs, and we will see how they get entrained by the flow, by these vortices. So there's a lot of very interesting ways of analyzing and visualizing data. Was there a question? All right. What we did with this study was we looked at optimizing this behavior of heaving airfoils. So we were able to discover very fast airfoils and very efficient airfoils and everything in between. So let's see, where is the last one? Yeah, a fast airfoil might, it would heave with a certain amplitude and frequency, and the intermediate one would have a different behavior. The arrows are again the velocity, not the velocity, the flow-induced forces. And then we have the very efficient one down there, which seems to be very slow, but it's very, very cost-effective. And it makes sense. The faster you go, the less energy efficient you become. Okay. And we were even able to discover, the different behaviors that give the same outcome. So these two foils actually end up moving with the same speed and same efficiency, but they have completely different behavior. The amplitude is different by 2 times. The frequency of heaving is also different by 2 times. Okay, and then you can analyze these things in a lot of detail. Why is it happening? How can I use this information to build small, what are they called? You know what I'm talking about? The small, very miniature flapping.
MAVs?
Yeah, MAVs.
MAVs?
Yes. Micro aerial vehicles. So you've probably seen. Have you seen videos? Do you know what I'm talking about? MAVs. Y'all are ocean engineers. You don't care about air. So let me show you. MAP dragonfly. MAP robot. Fine.
And with minimal surveillance mode for missions lasting is sufficient really for visual surveillance.
Okay, this is just a cartoon, but people have actually made these things.
For other platforms.
Okay. So you can use the results I was showing to figure out what's the best way of keeping to be very fast or be very efficient. I will find this. Was it Princeton? Where was it? APS, PFD, micro, air. Here, Harvard, not Princeton. All right. Right? You get the idea, but you can do cool things like optimize that motion, right? Instead of running thousands of experiments manually tuning things. So that's when simulations come in very handy. You can replace expensive experiments with simulations. There's many, obstacles along the way, but once you get there, it's all worth it. Okay. So more questions? No. All right. Okay. So should we start with vortex methods? We have 15 minutes. Yeah, we can start. All right. Let's. So at this point, you basically have everything you need to know to be able to do fluid simulations, whether with nice regular boundaries or irregularly shaped objects. And we've only talked about solving the momentum equation that has a velocity in there. But there are other ways of doing this. And one of the very nice ways of doing this is called vortex methods. Okay. Have you guys heard about these before? You have. You have. Okay, tell us something about this. Vortex methods.
Just yeah.
All right, you've heard about it. All right, have you heard more? Yeah. You nodded, so.
don't know.
Okay, so it's another way of solving the Navier-Stokes equation, another way of formulating the momentum equation. That's it. There's nothing special, right? So what we do is when we have our momentum equation. Oh, and the 2D results I showed you, vortex methods. The 3D results I showed you some time ago, the velocity methods that we have studied, the pressure projection method that we studied. Okay, so when we have the Navier-Stokes equation, how many times have I written this equation? It's, okay, so we have that, and what we do is we take the curl of the full equation, okay? And before I go on, let's just recall that, what is vorticity?
Kernel of U.
Vorticity is a kernel of U, okay? And what is kernel of U?
It's a matrix of I, J, K, partial over partial X, partial over partial Y.
That's it?
No, it's the I think, third.
UVW.
UVW. All right. This is just like computing a determinant, and so what we get is a method. So we get, what do we get? Is it clear what I did?
Yes.
Okay, if somebody doesn't know, ask. I'm just taking the determinant of this thing, this matrix. We have ith component, kill, oh, no, wait, that's not correct, there's a y. Yeah, you kill this and then multiply that, minus multiply that. Okay.
We.
Yeah, that's how I get the ith component. Then there's a minus. Kill that, multiply. Multiply the other one. And the last component is a plus. Kill these del v by del x minus del u by del y. Okay. Right, so this is the full three-dimensional velocity vector. What happens in 2D? I get rid of the kth term and then I'm happy. True or false?
So you have just the K, yes.
Or
True. You have just the third.
you have only the third term.
Third term.
All right, so what I said was wrong. I said you remove this and keep the I and j. If you have x and y, no, you keep the I and j and you get rid of the third one. So if you immediately jump to thinking of going from 3D to 2D, it's tempting to say, okay, there's no k term, so I and j remain. But if you look at it, there's a w here, which is 0 in 2D. There's a d by dz, which is 0 into the w d by dz. So these two terms are actually 0 in 2 dimensions. The only term that remains is dv by dx minus du by dy in the kth direction. Does this make sense? It's in the kth direction when I'm looking only at xy. So we have xy and 2d, which implies omega is dp by dx minus du by dy in the kth direction. Since w equals 0 and d by dz equals 0. Okay. So omega is something, and this is a one number in k. Does this make sense? How can I have a k direction 2D flows.
Normal to the plane.
Yeah, that's exactly true. So we have I, we have J, and we have K. Right? K is pointing out of the paper. It's a right-handed system. So the vorticity into D, it's all pointing out of the plane. Okay? Pointing out of the plane meaning the vorticity is rotating clockwise or anti-clockwise. Now the vorticity is rotating. The fluid is rotating clockwise or anti-clockwise. Okay? So into D, omega is a scalar. Omega is a scalar, meaning it has only one component, pointing either out of the paper or into the paper. Fine, okay, so let's see. Let's go back to our, let's go back to the curl that we were taking. This thing. All right, so let's see what will happen. The first term becomes so curl of momentum gives me del nabla cross u by del t plus nabla cross u dot nabla u minus nabla equal minus nabla cross p over rho plus nabla cross u square root. Okay. So let's simplify. What can we simplify?
So pressure term is okay.
Which one?
Pressure term.
It's minus nabla cross nabla p over rho. Yes, thank you. That's the mistake, right? Okay, so let's simplify. What does this become?
So omega by rho.
Omega over T.
What does this become? Yeah, this is a little more complicated, so we will separate it out and do it separately. Okay, what does this become?
Or del 2 del square over del square P.
No, it is not nabla dot. Nabla
Oh,
cross.
so it's 0.
0.
Right. Why is it 0?
It's perpendicular.
It's curl of gradient of a vector of a scalar, so that would be 0.
Okay, so you're saying 0, you are correct if rho is constant.
Yeah.
Rho might not be constant. So let's do it for the general term, very general case first, and then we will simplify. The third term actually becomes viscous diffusion of vorticity. And it's the same form as velocity diffusion. Okay. So A and B we will expand out and look at what they become. So let's see. Let's do B first. So B is minus nabla cross nabla p over rho. Okay? And when we use chain rule here, we have nabla 1 over rho cross nabla p plus 1 over rho nabla cross nabla p. Okay, I'll just use the chain rule. First, 1 over rho is variable 1, and nabla p is variable 2. That becomes derivative of variable 1 cross the other. And so, this term is actually equal to 0. This is the vector identity. And it's very easy to show. But this term becomes equal 1 over rho squared nabla rho cross nabla p. You know what this is called?
Yeah. The baroclinic term, baroclinic vorticity.
Yeah, this is called the baroclinic term. Baroclinic vorticity production term. Okay, so let's see. First, to convince you that this is indeed zero, let's do. How should I do this? Okay, we'll come back to baroclinic term. No, let's do. Okay, so baroclinic term is basically vorticity generation. Vorticity generation, which might be positive or negative, due to misalignment of density gradient and pressure gradient. Okay, and this term actually plays an important role in the formation of hurricanes. It displays important role in the shape form that hurricanes take. Okay. Now, why do we say misalignment? Nabla p is a vector. Nabla rho is a vector. If they are parallel, this term is zero. Right? The cross product is zero if the angle between them is zero. So only when there's a difference in the gradients, you will get a non-zero baroclinic term. Okay? And this non-zero, well, this difference in gradient can occur when if this can happen if rho depends on both pressure and temperature. Okay? Remember, P equal rho RT is the ideal gas law. So if rho depends both on pressure and temperature, you can have this misalignment. Okay? In barotropic conditions, the rho depends only on temperature, only on pressure. Okay, so whenever you see baroclinic atmosphere, barotropic atmosphere, this is what is meant. Okay, let's stop there. We will continue next class. Again, questions about homework, just email me. Or you can ask